So this is section 3.5, where we are going to be talking about transformations of functions. Now, before we get going, you need to know that this is a rather large section, and there is a lot of information that goes into it. So do not feel bad if you feel like you need to pause, stop, replay this lecture multiple times in order to comprehend the content. Okay? Now, also, if you remember from the last lecture that we did, I had made mention of the fact that these notes were going to be slightly different than the ones that had been uploaded to Blackboard previously. So this is one of those examples of where things are slightly different. Here, we're going to start out with the concept of increasing, decreasing, and constant functions. Okay? Now, in order to do increase, decrease, or constant, you need to focus on the domain. So we've already done an extensive discussion about your domain. So for you to recall, remember that your domain is the x values, or taking a walk along the x-axis. Okay? Now, we have three definitions that we have to follow. Your first one is this one here. It's for increasing. Increasing says for all a and b in the interval over ab, we have that if a is less than b, well, that implies that the function at a will also be less than the function at b. So essentially what that means is we are implying that wherever you started, when you draw along that graph, you're going to draw in that upward increasing motion, i.e. away from your body. Decreasing is the exact same definition. However, it implies that your function at A has to be greater than your function at B. So this means that wherever we're starting your graph, when you first start drawing it, decreasing would imply that you are drawing down towards you, or pulling your pen towards your body. Okay? The last one is constant. So constant essentially means that there is no change. So no matter what your x values are, your y value stays exactly the same. There's no change. So we have that if your a is less than b, then your function of a will equal your function at b. Okay? So one possible example that you may see is something like this, where you are given this graph here and you are asked to state your intervals of increasing, decreasing, and constant. So first and foremost, we have increasing, and so we have to look at where in our graph are we actually increasing in our values. Okay? So first and foremost, we need to look at all places where we would pull our pen away from us. You're going to start over on the left-hand side. Okay, so we're going to start looking here. And we are going to look at the graphs as individual pieces. So if we put our pen over here at the start, we've got this straight line that goes to a certain place and then stops. And then if you notice, we look a little different. So our next starts up here at this place, and we are going to travel down, but then we change directions. So in changing directions, we now switch, and notice my pen is going to come up in a different direction. So in this case, I am pushing or pulling away from my body. And then the last thing that we have is now we're going to start, and again, we're pulling in a downward direction. Okay? So those are the three things that are happening in my graph. So first and foremost, let's look at it. I want to know where I'm increasing. Increasing says I have to be traveling in this direction. Well, the only place I'm doing that is over this interval here, so my pink line, and we're using just the x values. So you see that this is going to start right here when x is 1. So here we're at x equals 1. And we are going to travel all the way through until this point here, which you can see is going to be this value at x equals 4. And so my interval of increase-decrease is going from 1 to 4. So hence, this is my interval right here that I'm using. And so this is my increasing piece. Okay. Now, when I want to look at decreasing values, okay, I'm looking at where am I going down towards myself. So I'm looking at going in this direction. Okay, so I've got 2 of them that are traveling in that direction. So I need to look at the intervals that that's happening. So this one here is starting here at x equals -2. And on the other side, we're starting at x equals 4. Now this is going to travel, of course, down to that change of direction point, which is at 1. So my first point of decreasing is going to be here at -2, 1. And then my second one is going to start here at x equals 4, and the arrow down here tells us that we are looking at x being positive infinity. So that makes this my second decreasing function. And since we have to write these as interval notation, we do just that. Now we have to look at the last piece, and notice this last piece is a horizontal line. So notice my arrow right here is telling me that I'm starting at x equaling -infinity. And I'm going to travel along my x-axis till I get here at -2, thus making the interval from -infinity to -2 my constant interval. Okay, so you are going to have to be required of knowing how to label your functions or label your graphs and identify where your intervals are increasing, decreasing, or constant. Now, another thing that we have to look at is called relative maximum and minimum values. Okay, so again, when we're talking about relative max and min, we are talking about your peaks or your values. Okay, so here we're talking about a relative maximum, and my relative maximum is going to occur at this specific spot right there. Okay, we're talking about that value. Now, since I only have the one peak, it means I only have the one relative maximum. However, when talking about my relative minimums, okay, which would be these over here, we have 2 of them because notice we have 2 valleys. So we're looking at this point here and we're looking at this point down here. So those would be our relative minimums. Okay. Now, the biggest thing that you have to keep in mind is that your value is the minimum or maximum specifically at the y coordinate. Okay. So, in other words, we would be talking about that value where we have, say, k equals. Okay. So you have to be required to know how to identify maximums and minimums, just like we did when we analyzed those quadratics. Now, a really important concept or larger concept that we have here is symmetry of functions. Now, when we're talking about symmetry, in other words, we are talking about reflections of your functions over an axis line. Okay? So we have 3 different functions and 3 different tests that we have to use to determine your symmetry. The first is what's called with respect to the x-axis. So with respect to the x-axis has these 4 concepts related to them. First and foremost, you're going to reflect specifically over that axis. Now obviously my graph picture over here kind of got off a little bit, but if you could imagine that this was sitting over your axis line, it would have been something like this, where you had your graph that went up in this direction and then down in this direction, and your axis is what cuts it in half. So you can think about if you are folding your paper along the x-axis, the top part of your graph has to match that bottom part of your graph. Now, one of the most important things when we're testing is that you're going to replace y with negative y and resimplify. If you have x-axis symmetry, then your simplification will give you back the original equation that you had. Okay. The other thing to notice about that is that if we're looking at point for point, your original point, its axis or its matching point will have the negative y value to it. Now the next type of symmetry we have is called respect to the y-axis. So that is going to be these four pieces of information. Again, if you look at your graph and you were to fold it right here along your y-axis, because that's what this is the y, and notice the stuff that's on the left is the same as the stuff that's on the right. In other words, its point matches negative x, y. So its test says that you need to replace all x's with a negative x and resimplify. When you do that, you should get back the original equation. Okay. Now the last one that we have is with respect to the origin. So that's going to be these ideas. So with respect to the origin is a rotation. It means you're going to spin it around 180 degrees and see what happens. Your straight point for point says that you should have the exact opposite of both the x and y's when you evaluate. It means you're going to replace both x and y with their negatives and resimplify. If you get the original back, then you have origin symmetry. So when we're looking at this graph here, we would say take this corner and we would rotate it 180 degrees down, and you would look to see, does this corner then end up down here? Okay. Well, in this case it does. Therefore you have respect to the origin. Okay. Alright, so knowing that, let's look at a couple examples. So here we have a couple of graphs. So let's look at the left one first. Okay. So let's look at this one first. And let's look at what we know. Well, first of all, if I look at my x-axis, so this axis right here, and I fold it along the x-axis, is what's on the top matching directly to the bottom? Well, clearly you can see the answer there is no. Therefore, you do not have x-axis symmetry. Now, what if we look at this axis here, your y-axis? Y-axis says the stuff that's on the left should match up identically with the stuff that's on the right. So if we were to look at that, does that happen? Well, in this case, no, it doesn't. So now, what if I grabbed my point right here and I spin it 180 degrees? So spinning it 180 degrees, do I get back what I started with? And in this case, it does. So this one would be considered to have origin symmetry. Okay. Nothing more to it than that. So let's do another one. Okay, so this one's number 2. Again, let's look at x-axis symmetry. So if we draw along our x-axis, is what we have on the top matched directly to what we have on the bottom? Well, the answer there is yes. So we know for sure that we at least have x-axis symmetry. Now, we can't stop because you might have one of the other symmetries or all three as well. So we have to test them all. So if we look here now at my y-axis symmetry, again, the stuff that's on the left should match the right. And does that happen? Well, in this case, that answer is no. And if I put a point, say, right here, and I spin 180 degrees, do I get back what I started with? Well, in this case, again, no, because spinning at 180 degrees would put the object over here, and I don't have an object over there. Therefore, the only symmetry I have for this one ended up being x-axis symmetry. Now, what's important to remember is you can have one symmetry type, you could have two symmetry types, or you could have all three symmetry types within one graph. So you do have to test all three symmetries before you can definitively state what you have. Now, the other thing we have is we have this example. And this example says, find the point that is symmetric to the given point. So the given point is going to be the point 8, 3. And I want you to find its symmetry values with respect to the x-axis, with respect to the y-axis, and respect to the origin. So if we look at the x-axis, y-axis, or origin, what you have to remember is that all three of these have a rule. My first point has to start with the rule. And the rule for my x-axis says that whatever my y value is, its symmetry point is the negative of that. So if we look at that idea, my original point was the point 8, 3. Therefore, its symmetry point has to be the point 8, negative 3. Now when we talk about y-axis, we are talking here about the point where I have negative of my x, but my y stays the same. Therefore, its symmetry point has to be negative 8, 3. Last, we have your origin, and your origin says you have to have the negative of both points in order to be origin symmetrical. So therefore, we have the point negative 8, negative 3. And that is all you would have to do, essentially, in order to show what your symmetry points is. I'm looking at this part right here, being able to show what the original point was and what its matching points came out to be. Okay. Now, changing gears a little, we have a concept called even or odd functions, even, odd, or neither. So first and foremost, we have determining even functions right here. Graphically, an even function is symmetric with respect to the y-axis. So if you are given a visual representation of that graph, then you are looking for y-axis symmetry. If you have it, then you're done. You can state that it is even. Algebraically, though, we are looking at replacing all x's with negative x and resimplifying. The goal is to get back your original equation, thus using this formula right here, where we are looking at if I input negative x into my function, will I get the same function back? If I do, then I have an even function. If I don't, then I might have something else. An odd function So to determine odd functions, again, we can look at it graphically. So graphically says we are looking at with respect to the origin. So we are looking for rotation 180 degrees in order to see if you have an odd function. It also means that if you input the negative x into your function, then you should get the exact opposite spit out of that function. Okay? If that's what happens, then your function is odd. Okay? Now, we have 3 tests because you have 3 possibilities. You can either have even, odd, or neither. So if you look at it, your test is going to be inputting negative x into your function and seeing what happens. That's what we're testing. An even says that your result that you get back was the same. Odd says the result you get back is the exact opposite. Neither means something totally different occurred, and therefore you have neither even nor odd. So what you're going to have to do is you're going to have to be able to work problems where you determine not only the symmetry, but you also have to determine even, odd, or neither, as well as intervals over which they are increasing, decreasing, or constant. So everything we've talked about thus far. So let's work an example. So we have that you need to sketch the shape of the relation and then determine the following. Is it a function? Yes or no? If it is a function, is it even, odd, or neither? And then, does it have y-axis symmetry, x-axis symmetry, origin symmetry, or none? And then find the intervals over which you are increasing, decreasing, or constant. So the first thing you need to do is we're looking at the absolute value and then plus 3. So the smartest thing to do would be to create your XY table, which is going to allow you to graph. Okay, so again, we're going to have x, and then we have that f of x is the absolute value of x plus 3. And so we're going to pick our x values, and we're going to determine their y value counterparts in order to create a graph. So the first place that I would start again is at the origin. So I've got the absolute value of 0 plus 3 is going to give me 3 as a result. Then from there, I would go 1 to the left and 1 to the right. So here I would pick 1. So I've got the absolute value of 1 plus 3 is going to give me 1 plus 3, which equals 4. And then I would look at negative 1. So the absolute value of negative 1 plus 3 gives you 1 plus 3, which gives you 4. As remember, when you take the absolute value, it doesn't matter if you're positive or negative going in, you are positive coming out. So I have 3 coordinate points here, so I'm going to start putting together my graph. So I have the point 0, 3, so 0, 1, 2, 3. I then have the point 1, 4, so I'm going to go over 1, but I'm going to go up to 4. And then I have the point negative 1, 4, so negative 1 up to 4. And I've got my lines. Okay. So to help make it visual, I'm going to go ahead and use a ruler, although you don't have to if you don't want to. Remember, you have to have 2 coordinate points in order to graph a line. So I'm going to go ahead and graph this line. Going the one way, and then I'm going to go ahead and graph it going the other way. And so this right here is my graph. Now, based on this, I have to look at, is it a function? And remember, to tell if something's a function, we have to use the vertical line test. So in this case, we know that yes, it's a function, and because it passes your V test. Okay, that's what's going on and what it's why it's happening. So now we need to look at it, and we have to be able to determine even, odd, or neither, as well as its symmetry. So let's start with the symmetry part. Symmetry says, do I have x-axis symmetry? So in other words, if I look at my x-axis, is the same thing on the top happening on the bottom? Well, the answer here is no. Y-axis symmetry says I'm looking at my y-axis here, and is the same thing on the happening on the right? Well, in this case it is. So we have y-axis symmetry. And of course, if I grab this and spin 180 degrees, do I get the same thing back? Well, in this instance, it would be no, I don't. So the only symmetry I have here is my y-axis symmetry. Now, using the definitions of even, odd, or neither, because I have y-axis symmetry, it also means that I have an even function. However, let's prove it algebraically. So to prove even, one thing that I know is that I have to take my function and evaluate it at negative x and look to see what happens. I want to test to see, do I get the original back? So this is what I am testing for. So I'm going to take my function of negative x, and I'm going to input it. So this becomes the absolute value of negative x plus 3. Well, once you do that, you need to evaluate. Well, what do we know about absolute value? We know the absolute value of the negative is going to be the same as the absolute value of the positive. Therefore, in this instance, you do end up with the original back, thus proving that you are even. Okay? So that is one way to look at it algebraically versus looking at it through your symmetry. Now the last thing that we had to look at is your intervals of increase, decrease, or constant. So the first thing we need to note is when you're looking at this, do we have any constants? Well, remember, constant means horizontal line. And in this case, that answer is no. So when we're talking about constant here, we have none. Now, I want to know where we are increasing and where we are decreasing. Okay? So, we have to start over here on this leftmost side, and we are traveling in this direction. Okay? So when we do that, we're going to go ahead and put our pen down, and as we travel, put it on the top of your graph. And as you travel, what happens? Well, we are traveling in a downward motion. Because we're traveling in that downward motion, it means to start with, we are decreasing. The arrows out here mean that we are talking about x being negative infinity, and we are decreasing all the way until we get to our change in direction point. So here we're looking at x being 0. So, because we're looking at the x-axis, so we're going to look down, and that means our decreasing is going to go from negative infinity to 0. And now we need to look at what happens when we change directions. Well, when we change directions at this point, now we are drawing up and we are going away from us. This is now a positive or increasing motion. The arrow up here says that we're going to x being positive infinity, which means we are increasing from where we changed directions, 0, up through positive infinity. Okay? Now that answers everything that we needed, so I have analyzed this function completely and fully. Okay? Alright, so now let's look at another one. So we have x equals negative y squared. Okay? So x equals negative y squared. Well, the easiest thing to do, again, is going to be to create an x and then y table. Let's see. No, that's not going to be the easiest way. In this case, what we're going to do is we're going to want to choose y values in order to get your x value. Okay. So we're going to create this table a little bit differently, and here we're going to choose y values to dictate the x. Okay, so sorry about that. Alright, so here the first thing I would do is I would start what happens if my y is 0. Well, we have to plug it in. So this is negative of 0 squared, which gives me a 0. Now I'm going to go ahead and look at what happens if y is 1. So I'm going to plug it in. This is negative of 1 squared. 1 squared is 1. Apply the negative and you get negative 1. Now let's look at negative 1. So this is negative of a negative 1 squared. Negative 1 squared is 1. Apply the negative and you've got negative 1. So let's start graphing what we have and see what's going on. So we have the point 0, 0. So we have this point here. And then we have the point that y is 1 and x is negative 1. So we have this point here. And then we have the point that y is negative 1 and x is negative 1. So this point here. Now I'm going to do just a couple more, 2 more points to be exact. I'm going to do 2 and negative 2 so we can really see the change. So we have negative of 2 squared. Well, 2 squared is 4. Apply the negative, gives you a negative 4. And then negative of a negative 2 squared. Again, negative 2 squared is positive 4. Apply the negative, you get a negative 4. So here, when y was 2, x is negative 4. 1, 2, 3, 4. And when y is negative 2, we're at negative 4. Okay. So if you look, it should be clear that what we actually have going on here is this parabola-like shape. And this should make a lot of sense because, after all, this right here is a quadratic equation. It's x equals negative y squared. Now, in order to answer the question, is it a function, remember your vertical line test. So we have to drop a line in, and what do you notice? Well, what you should notice is that this vertical line is crossing at 2 places. Therefore, this is not a function. You fail the v-test. Okay. Now, because this fails, it means I don't have to do all those other steps. I don't have to find the symmetry. I don't have to find even, odd, or neither. I don't need to state intervals of increase, decrease, constant because I'm not a function. I'm just simply a graph. Okay. Now, the last one I wanted to work through is a cube. Okay. So this is going to be h of x equals 2x cubed. So again, one place that I would start is I would start now with your table. So here we can do x and then f of x equals 2x cubed. So again, I'd start with 0. So this becomes 2 times a 0 cubed, which is 0. And then I'd make life a little easy. I would choose 1 and negative 1. So I'm going to have 2 times a 1 cubed. Well, 1 cubed is 1 times 2 gives me 2. Now I have 2 times negative 1 cubed. So negative 1 cubed is negative 1 times 2 gives me a negative 2. Now just to make sure we're following along, I'm going to then also use 2 and negative 2, and that should give me enough points to clearly see what's going on with my graph. So here I'm going to have 2 times 2 cubed. Well, 2 cubed is 8 times 2 is 16. And then I'm going to have 2 times a negative 2 cubed. So negative 2 cubed is negative 8 times 2 is a negative 16. So I now have everything I need to graph, so let's take a look at that graph. I'm going to start with the point 0, 0. I am then going to go over 1 up 2. I'm going to go negative 1 down 2. And then my next points are going to be way off the chart. So I have to add a little bit of a curvature here. And we're going to go straight up, and then I'm going to curve it a little bit down in the bottom, and we're going to go straight down. So remember, your cube graph kind of looks like a cubic that's been twisted in the middle. So now let's start in. First and foremost, is this a function? Well, if I drop a horizontal line anywhere in my graph, I only touch it one place. Therefore, yes, this is a function, okay, because it passes the v-test. Therefore, because it's a function, I need to fill out the rest of it, which means I need to know even, odd, or neither. I need to know my symmetry, and I need to know increase, decrease. Okay. So first and foremost, let's do the easy one. Let's look at symmetry. If I were to fold this graph here along the x-axis, is the same thing that I have on top matching identically to the bottom? Well, the answer there is no. If I were to fold it along this y-axis, is the same thing that I have on the right matching to what I have on the left? Well, again, the answer there is no. Now, what if I grab a hold and I spin this 180 degrees? Do I get back what I started with? Well, that answer is yes. So this has origin symmetry. Okay. Now, based on origin symmetry, we can apply our definition of even, odd, or neither. And what you will notice is that this is actually an odd function. We can prove that algebraically by very easily running our test. So, if we take our f of negative x, what we should get is the opposite of what we started with. So we have 2x cubed. So we're going to do this as being 2 times the negative x cubed. When we simplify this, negative x cubed is a negative x cubed times 2 is a negative 2x cubed. Is this the exact opposite from what we started with? Well, that answer is yes. Therefore, this is an odd function. Okay, so that proves odd. Now, the last thing we have to look at is increase, decrease, and constant. Well, when looking at this graph, do I have any horizontal lines? Well, the answer to that is no. Therefore, when we're looking at constant, for this graph we have none. Now, again, remember, we have to start on the left side, and we are going to be traveling across my x-axis. So we're going to start down here, of course, because this is the leftmost side, and this arrow here is telling me that x is negative infinity. And when we do this, I'm traveling in an upward direction. Okay? So if you look at this, if we start down here and we start moving across the x-axis, I am traveling upwards in an upward direction. And I'm going to keep on traveling upwards the whole length of the entire graph. At no point did I change directions. Well, this part here is where x is going to be my positive infinity, because it's just going to keep on going forever. Therefore, my increasing is going to be over the interval negative infinity to positive infinity. Since my increasing interval uses the entire graph, it means for decreasing, I have none. And therefore, again, I have answered everything that I have to be able to answer out of this particular problem. Okay? All right. Here's the biggie, the actual transformation or translation of functions. So we have these parent functions, and some of you may remember from high school, we initially called, like the big top ones. So we had linear, absolute value, quadratic, square root, cubic, cube root, and rational. Okay, so these were kind of the big ones to start with. Well, there's also quite a few others that exist, but we just care about the basic ones. So when we're looking at the functions that we care about, we care about linear, absolute value, quadratic, square root, cubics, cubed root. And those are kind of the big six that we care about. Now, you do kind of have to know that these ones exist, the fraction, but I don't like to try and focus on it. But they are there. Okay. Alright, so we have to look at how are we actually going to try and start to find some of these. Well, first and foremost, we have an order. And in Hawks, it is imperative, it is mandatory, it is extremely important that you follow this order completely. Don't get out of order, don't get out of sync. In Hawks, in order to get your graphs correct, especially in your homework and potentially an online exam, in order to put a translation in correctly, you first need to do the horizontal shift. Then you will put in any horizontal or vertical stretches or compressions. You will then look for any horizontal or vertical reflections. And then lastly, you will put in your vertical shifts. Okay? Now, that being said, there are three types of translations that we have to deal with. Okay? The first one here is being your shift. Shift means you're moving either left or right or up and down away from your origin. Okay? Second, we have a reflection. Reflection essentially means negative sign. Okay? So it means somewhere in your graph you've got a negative. Compressing and stretching is where you are either pulling away or squishing towards your axis lines. Okay? So those are the three types. In your notes that you can print off, you got these pictures, which are just examples or basic examples of the different types of translations. So this first one here is showing you translating to the left or right. So notice the solid line here is going to be that base function that you started with. This dotted line right here was a translation shift to the left. And the dashed line on this side was a translation shift to the right. This middle graph here is where we are going up or down. So again, notice the solid line is where we started from. The dotted line here is a translation down, and the dashed line is a translation up. Okay. On this third graph, we have a reflection over the y-axis. So this was the y-axis, is right here. This solid line here was the original, and so essentially what we've done is folded the axis along the y-axis and stamped the exact same graph over on the other side. So this dashed graph here was your reflection over that x-axis or over that y-axis. If we go straight down below it, you can see that we have a reflection over the x-axis. So your solid line here was the original, and this dashed line here ends up being the reflection. Again, x-axis means we took this x-axis and we folded along it, and this is what happens. Now these last two over here are representing your shrink or stretch, depending on if you're looking at it vertically or if you're looking at it horizontally. Okay, and again, you are either going to squish towards that axis or you're going to pull away from it. Okay. So let's look algebraically at how some of this is going to work. Okay. So first and foremost, we have shifts. So how do we identify a shift out of our equation? Well, this is where we are looking for your addition or subtraction. So we're looking for the add or subtract. Specifically, in my vertical, I have two options. I have what's called shift up, and I have shift down. In order to shift up, says I'm going to take my equation, so y equals whatever my function is, and then I'm going to add a value to it. The plus b part means we're shifting up. Shift down says I'm going to take that same equation, and in this case I'm going to subtract some constant from it. Okay. Now, the other thing, or what we have on the other side, is we have where I can shift to the right, or I can shift to the left. Shifting to the right says that I'm going to take my function y equals f of x, and what happens is now we are inside, so we are going to subtract some constant. Shifting left says I'm going to take my function, and in this case I'm going to add a constant. Now what's important to notice here, when we shift right, your d value is positive. So remember, inside the bubble your signs are opposite. That means left says that your d is negative. Okay. So all in all, what is it that we have to take away from here? Well, we have to take away that we have two types of shifting. We have vertical which is equations written as y equals f of x plus or minus b, and we have horizontal. So y is going to be f of x plus or minus d. Okay, that is shifting. Now let's look at reflections. So again, how do we notice or recognize your reflection? Well, a reflection is going to be where you are multiplying by -1. Okay? i.e. you've got that negative out in front. So with your reflections, we again have vertical and we have horizontal. Vertical reflections say that you are going to reflect over the x-axis. It means that if your function started out as y equals f of x, then a reflection would be listed as negative f of x, where the negative is here, it's out in front. Okay. Now we can have horizontals. Horizontals are where we are going to reflect over the y-axis. So this says if y equals f of x, then my reflection would be f of negative x. Notice the negative is now inside your parentheses or bubbles. So what does this actually mean? Well, again, we have horizontal and vertical. My vertical says y equals negative f of x. It is an outside translation. My horizontal says that y is f of negative x. It's an inside or internal translation. The last thing that we have is your stretch and compress. Stretch and compress is where you multiply by a constant. So a constant meaning a number, but that number is going to be the positive. So when we're talking about compressing, we're not talking about the sign. We don't care about the sign of the value. We just care about the value itself. So we have horizontal and vertical, just like before. But with each of those, we have a stretch or a shrink component. When we're talking about verticals, if we want to talk about a vertical stretch, we are talking about whatever your value is has to be greater than 1. So it has to be a whole number. Okay? So that's what we're talking about here. We're talking about a whole number. To shrink a vertical says we're talking about a fraction. So we're looking at values that fall between 0 and 1. The actual definition we use says for all values greater than 0, the graph is either squished or pulled away from the x-axis. So when we're talking about verticals, we're talking about squishing or pulling something away from that x-axis. Horizontal is going to be the exact opposite. So to stretch a horizontal says we are looking at the fraction. So we are looking at values that fall between 0 and 1. And to shrink it says we are looking at the whole numbers. So values to be greater than 1. It also has an identical definition that says for all values greater than 0, the graph is either squished or pulled away from the y-axis. So here, when you're talking about your horizontal, we are talking about getting further and further and further away from that y-axis point. Okay? So how does that actually look in terms of your equation? Well, when we have our vertical, we are talking about y equaling a times f of x. Notice a is on the outside, and notice it is just simply a positive value. When we have the horizontal, we are talking about y equaling f of cx. Notice it is being applied inside directly onto the x, so it is an internal. The biggest hint I can give you about deciphering these is the following. If your operations or your values are occurring on the outside of your parentheses, then you have a vertical representation. If your operations, your values, your reflections, your negatives, your constants, if all of that is being applied inside a parentheses, then you have a horizontal look to it. Okay? So that's the biggest advice that I can give you. So here, what we're going to do is we're going to look at a couple examples in terms of what it is that you need to be able to do yourself. Okay? All right. So first example. It says for each function, determine the basic function that has been transformed, then identify each transformation and what it will do to the basic function. Graph the basic function and each transformation. Determine the domain and range of the transformed function. So we have the cubed root of x plus 5 minus 2. So the first thing we have to do is we have to know what is that base function. Well, the base function is going to be like one of those parent functions. So here, my base function is going to be the cubed root of x. And everything else in the equation is being done specifically to the cubed root of x. So I have to look at what is actually being done. So the first thing you want to look at in Hawks is your horizontal shifts. So the first thing you need to look for is, do you have any horizontal shifting? Remember, horizontal shifting has to do with adding or subtracting, and horizontal is an internal, which means we're looking at something inside your parent function. Okay? Well, in this case, I am going to horizontally shift 5 units. Notice this 5 is internal, and because we are shifting horizontally, it means we have to determine, are we going left or right? Well, here I've got a plus 5, which means if you refer back to what we said, when D was positive, we shifted to the right, but if D was negative, we shifted to the left. Well, remember the base equation was x minus d meant shift right, x plus d shift left. Here I have plus a constant, or plus d, so we are shifting to the left. So here my horizontal shift is going to go left, and by how much? Well, it is 5 units. The next thing that we have to look at is we have to look at all of your reflection. No, not your reflection. Sorry, we have to look for your stretch or compress. So we are looking at if you have any stretch or compressions going on. Okay, that's the second thing you got to look at. Remember, stretch or compress is where we are looking for a constant. Are you multiplying by a constant value? Well, the answer there is no, because I have nothing on the outside and I have nothing directly on the x. So here I don't have any. This is none. Now I need to look at, do I have any reflections? So remember, your reflection is the negative sign. So if I'm looking at the front of my function here, do I have a negative? Well, the answer is no. And then I need to look directly at the x. And do I have a negative there? And the answer is no. So here, I do not have any reflections. The last thing I need to look at is my vertical shift. Well, remember, vertical is we're looking for addition or subtraction on the absolute outside of my function. So here, I have a -2 going on. Therefore, my direction is that I am shifting down, and I am shifting down by 2 units. So now I have to start working on graphing my translations. So the important piece that you need to do is, 1, you need to be able to graph your base, and then 2, you need to be able to graph your final. So like your final after all your translations have occurred. So first and foremost, we need to graph the base function. Okay? So we are looking at the cubed root of x plus 5 minus 2. So first and foremost, we need to look at the cubed root of x. So there's a couple things you could do. You could create yourself your xy table, but you just basically have to be able to graph it however you see fit. Okay? So if we did an xy table, we would do x and then f of x equals the cubed root of x. And when we want to look at points that we know we can take the cubed root of, so first I would start with 0. So the cubed root of 0 is going to be 0. And then I would look at 8, because I know the cubed root of 8 is going to actually be 2. And I'm going to look at negative 8, because I know the cubed root of negative 8 is also going to be a negative 2. So I'm going to graph those as my base function. So I've got the point 0, 0. And then I have the point 8, 2, so out 8, up 2. And then I have the point negative 8, negative 2. Okay. So I've got to put a slight curve into this, and we're going to keep going. And then we're going to come down, and we're going to keep going. Okay. Now, because you're graphing more than one into your graph, you need to be able to label it. So in this instance, I used a color, and I used black. Now you can label it however you choose, but I'm using colors. Now, the other thing that we need to be able to do is we need to be able to graph what you've got. So now we have to have f of x equals the cubed root of x plus 5 and then minus 2. So you want to be a little smart, okay? Because we are dealing with x plus 5 under this radical now. So we want to kind of use values that are going to help us out. So the first thing is I would be looking at, what do I know that I can actually take a cubed root of? Well, I know that I can take the cubed root of 8. So 5 plus what gives me 8? Well, 5 plus 3 gives me 8. So this is the cubed root of 3 plus 5 and then minus 2. 3 plus 5 is 8. So the cubed root of 8 is 2. Minus 2 gives me 0. Now I need to look at another value. So again, I want to look at, what do I know that I can take the cubed root of? Well, I know that I can take the cubed root of 0. So what plus 5 gives me 0? Well, negative 5. So if I look at negative 5, I have the cubed root of negative 5 plus 5 minus 2. So negative 5 plus 5 is 0. Cubed root of that is 0. Minus 2 gives me a negative 2. So I'm going to start looking at these points on my graph so I can kind of see a little bit of what they look like. So I have the point 3, 0. So 1, 2, 3, 0. So that's this point right here. And then I have the point negative 5, negative 2. So 1, 2, 3, 4, 5, 1, 2. So that's this point right here. And I'm not quite sure yet how these are going to connect. So I have to keep going. So I need to know another value that I can get here. Okay. Well, you could start using any points you want. You just have to remember that you may be graphing fractions, so you just have to be careful. And some of this has to do with, you need to know what your cubes are. So we know that 2 cubed was 8. We know that 3 cubed is 27. So if I wanted to know what I could use to get 27 in there, I would have to use 22. So here I could look at x being 22. Obviously that's going to be way off my chart. So you just have to kind of be smart with your numbers themselves. Okay? And what you're looking for is what's actually happening. Now, let's look at what were to happen if I used negative 7 and see what we get. Okay? So negative 7 plus 5 is a negative 2. I'm going to take the cubed root of a negative 2 and get an answer, and then subtract 2. And this is going to give me, so I've got the cubed root of negative 7 plus 5 minus 2. It's going to give me roughly negative 3.25. So negative 7, and I'm at 123.25. So notice I've started coming down. Okay. So what I think is happening here is that this clearly is coming up like this, which means we have to go down. So here this was at 5. So if we're looking at that, then I would look at 9 and see what happens at 9. So negative 3, I've got negative 9 plus 5 minus 2. So we have the cube root of -9 plus 5, and then we're going to subtract 2, and this is -3.58. So here at -9, we're down even a little further. So what we're doing is we're coming down in this direction. Okay? So we've kind of sort of graphed. Now that is using a table. The other way that you could approach this would be, if you look, we need to take this middle point here. We need to shift it left 5. 1, 2, 3, 4, 5. And then we need to shift it down 2. So it would go right here. You then have to take the other points you graphed and do the same thing. So whether you use a table or you just simply move them is completely up to you. So for example, this point here, we would have to move in this direction. We would move this direction -5, and then we would move in this direction in -2. So if you notice, 1, 2, 3, 4, 5, 1, 2, look, there we go. That's the red point that we found. And so on and so forth. So it's up to you how you graph these. Now the cool thing about Hawks is all you have to do is put this information here into the program and it graphs it for you. But you do have to know kind of the basics on how you would graph them for yourself. Okay, so let's do another one. We have 1 minus the absolute value of 4 minus x. So here, the first thing we need to do is we need to again identify that base function. And in this case, we're dealing with the absolute value of x. Now the other thing that I would do is I would notice and look that this right here is actually a shift. And so not only is it a shift, but it is vertical. Why? Because it is on the outside. So I would actually rewrite my function so that it reflects that it is vertical. So I'm going to rewrite this function to say negative absolute value, and I'm going to leave my middle alone for a minute, and this is a +1, so this is going to be +1. Now, the other thing that you need to notice is that this part in here has been rearranged. So I also would want to rearrange to show your shift and reflection. So here I would rearrange this one on the inside to write your x first. So notice this is a -x. So this is -x, and that's a +4. So +4. Once you've rearranged, you can then go ahead and start identifying what you have going on here. So again, the first thing you need to look for is a horizontal shift. Well, in this case we do. Okay, with the horizontal shift is right here. It's a +4 because it's inside. Remember, that means opposite sign. So this means that we are going to shift to the left, and we're going 4 units. Now the second thing we need to look at is stretch compress. And in this case, we have none, because I don't have a constant multiplying at any point. Now the third thing we need to look at is our reflections. And we need to look at what exactly do we have going on. Well, reflections are negative, so notice I have two of them, one here and one here, which means I have both a horizontal and a vertical reflection. So I have that first I'm going to reflect over the x-axis. Then I'm going to reflect over the y-axis. The fourth thing I need to look at is if I have vertical shifts. And in this case, again, I do. We put it out and back. And because it's positive, this means we're going to go up by 1 unit. Okay. So I need to graph the original. So my base equation, again, is going to be absolute value of x. So we know the absolute value of 0 is 0, the absolute value of 1 is 1, and the absolute value of negative 1 is 1. Again, this is that v. So we're going to go ahead and graph this line so that we can look at that base function as it is. Okay, so we're just going to go ahead and drop these in. Again, remember, make them close. I'm using a ruler to make it easy. And now, in this case, we need to go ahead and figure out where the end result is going to be. So the first thing that has to happen is we have to shift left 4 units. So if we do this based on just simply shifting, take this first point that we started with, and it has to move to the left 4 units. So 1, 2, 3, 4. That puts it right here. That also means each of these has to shift 4 units. So if we start with this one, 1, 2, 3, 4, puts it here. And this goes 1, 1, 2, 3, 4, puts it here. And so this would be my horizontal shift. Now from here I don't have any stretch compress, but I do have reflections. So the first reflection that I have is to go over the x-axis. So this is my x-axis line. My x-axis line says that I'm going to fold my axis along that line, and I am going to go ahead and reflect it down. So this point stays the same, but this point comes here, and this point comes here, making this that new graph based on the reflection. Now I also have to reflect over the y-axis. So this is my y-axis, which means all these points here have to come to the other side. So this first point is at the point negative 4, 0. So it's going to reflect over here to negative 4, 0. This point is going to be at the point negative 5, negative 1. So this comes over to 5, negative 1. And then this other one is at the point negative 3, negative 1. So it comes over to 3, negative 1. So then this becomes my new graph potential. And I'm giving it a zigzag just simply so it looks a little bit different than the other. So then, foremost and final, we then have to shift it up 1. So everything has to go up 1. So this point is going to come up here. This point here comes up 1. And this one comes up 1. And because that was the last thing I had to do, then that means we have now completely finished the graph. So I'm going to go ahead and draw this one in as a larger graph. Okay, there we go. Slap my arrows in the bottom. Okay. And so now I have to label what I have. So what I have here is I have this as my base, so this one is y equals the absolute value of x. And then I have my actual graph. So this one down here is that y is negative absolute value of negative x plus 4 plus 1. Of course, I kind of ran out of space. I probably could have done that better. But there, at least it's labeled. Okay, so that is what you have to do. And this is what it might look like if you go ahead and just simply graph it using the coordinate points at hand. Okay, instead of, or using your translation, instead of doing an XY table. Okay. Okay. So let's look at another one. Here again, we can look at your base. And my base is going to be the absolute value of x. So again, I need to look, and in this case, there's nothing I need to rearrange. So the first thing I have to look for again is that horizontal shifting. Horizontal shift is that internal shift. And that internal shift in this case happens to be the 1. And because of the subtraction sign, this tells us that we are going to the right by 1 unit. We then need to look at your stretch compress. Okay. And again, in this part, my stretch is internal. It is a fraction. So when we are talking about an internal fraction, we are talking about a horizontal stretch. So here we've got a horizontal stretch. And in this case, it's by a factor of 1/2. Then we need to look at your reflections. And here we do have one. Again, it is an internal reflection. So an internal reflection means that we are going to be reflecting horizontally. So we are going to reflect over your y-axis. And then the fourth thing that we're looking at is any vertical shifts we have. So in this case we do. If you look, we've got this +2 off the end. So here we are going to go up by 2 units. Okay? So that is everything that we have. So the first thing we need to do is we need to graph the original. So again, my original is the square root of x. The square root of 0 is 0, so we can start it right there. Because it's a square root, I can't have negative x values, so I'm only looking at the positive. And I want to make it easy. So the first thing I'm going to look at is x is 4, because I know I can take the square root, and that gives me a 2. And then I may look at 9, because I know when I take the square root I get a 3. 1, 2, 3. And then this right here is going to now be my parent function. Notice it's got a little bit of a curve. So now I need to be able to graph the others. So first and foremost, I've got this horizontal thing here. So my horizontal shift to the right says I'm going to take all these points and move them over 1. So this one moves over 1. this one moves over 1, this one moves over 1, and I kind of have this little graph thing that's going right about here. The next thing I have is a horizontal stretch by a factor of 1/2. So what's happening here is your horizontal stretch is talking about the direction that you are moving in terms of your axis lines. So you are essentially we're essentially pulling my graph away from the axis. So a horizontal stretch is talking about pulling that graph away from your y-axis. Okay, so we're stretching it like taffy. Well, we're doing that by a factor of 1/2. Okay, so when you look at, say, your point here at 0, if you're trying to take 1/2 of it, you've got nothing. I mean, it can't get any closer or further away from the axis because it is already sitting at the 0 line. However, this new point here, if we're looking at this y distance, it can shrink by a factor of 1/2. So here it would do just that. It would shrink by its factor of 1/2 and down. Now this distance over here is a distance of 3. So if you look at shrinking that by a factor of 1/2, we would put our new dot kind of right about here. And so this would be that new shrinking line. Now the other thing we have to do with it is we have to now reflect this over the y-axis. So all of these points here have to come to this side. So we're here at the point 1, 0. So it's going to shift over to -1, 0. Here we're at the point 5 and 1. So we're going to come to -5 and 1. And then we're at the point 9 and about 1.5. So we're going to go -9 to 1.5. And again, this kind of becomes that new line that we got. And the last thing is that we have to shift it up. And we're going up 2 units. So we're going to take this point and we're going to go 1, 2. And this is going to be right here. Then we're going to take this point and we're going to go 1, 2. So it's going to go here. And we're taking this half point in the middle and we're going to go 1, 2. So it's going to go right here. Which means this, so excuse me while I'll turn it sideways, this right here is going to be your result line. Okay, so this is the line that we are now actually talking about as being the translated line. So again, if we kind of input what we've got, we have this one over here is going to be the square root of x. And then we have that this line right there is going to be the square root of -1/2 x minus 1 plus 2. Okay. Alright, let's look at another one. Alright, here, if we're talking about our base, we are talking about x squared. And so we're doing everything onto x squared. So again, the first thing you need to look for is your horizontal shift. So here, do I have one? Well, I do. It's inside the parentheses. Because it's a plus, it tells me I'm going to the left. And how far? Well, I'm going 1 unit. Second thing I need to look at is stretch compress. So that is multiplying by a constant. In this case, my constant is on the outside. Remember, outside means that it is a external translation. External translations are vertical. And this, in this case, is a whole number. So our vertical stretch compress at a whole number means we are stretching it. So we are going to stretch vertically by a factor of 2. The next thing we need to look at is do we have any reflections? And this time the answer is no. We don't have any negative signs anywhere. So the last thing we need to look at is your vertical shift. Well, remember, verticals are on the outside, and this is a +2. So we have a vertical shift up 2 units. So now we need to graph. Again, this is a quadratic, so remember 0 and 0 squared is 0. And then if we look at 1 and -1, you get 1 as a result. And then if we plug in x is 2, well, 2 squared is 4, and -2 squared is 4. So we've got our basic parabola shape, which is this shape kind of right here. And we're going to bring this up, and then do this side over here, bring that up. So now we need to look at moving it. So the first thing we need to do is move it left by 1 unit. So we're going to shift all of our points over to the left. So here's 1, here's 1, and here's 1. And then we're going to go, here's 1, and here's 1. So we've kind of got this little shape right here is our first shift. So I'm kind of drawing it light so that you can just see what's going on with it. Now we have to do our stretch compress. So remember, we are doing a vertical stretch by a factor of 2. So when we're talking about a stretch, we're talking about pulling it away from that x-axis. So in this case, what's going to happen is your graph is going to get skinnier. Okay, so it is going to pull away from that x-axis, kind of like taffy, and get skinnier. So we have to look again at your y distance. And so we have to kind of multiply by it because we want to get further away from your axis line here. So stretching it says that I'm going to take this first point, nothing happens. But when I look at the second point, we're going to start to make some changes here. Okay? And those changes are going to be the fact that if we look at this point here, this point is at y equals 1. Well, we need to multiply that by 2. So instead of it being at 1, it's going to come up here to 2. And then we also need to look at the other side. So instead of it being here again at 1, it's going to come up to 2. So what you would see is that it's getting skinnier. Here we're up at 4. When you multiply by 4, you get 8. So instead of this being at 4, okay, now it's going to be all the way up here at 8. And then again, same on the other side. Instead of it being here at 4, we're going to be all the way up here at 8. And so we've got this new skinnier parabola kind of going on here. So notice things are starting to get a little tight. Okay, but so that's what's going on with that. And then the last thing that we have to do is we have to shift this up by 2 units. So we're right here. So in order to shift it up by 2 units, we're going to go 1, 2, so we're going to start here. And then we need to go to our new point, so it's this point here, and we're going to come up 2, so it's this point right here. And then on the other side, we're going to come up 2, and 2, so it's this point right here. And then from this one, we're going to go up 2, so 1, 2, that makes it right here. And so same, 1, 2, puts it right here. And so this is going to be my new graph. Okay. And so you can notice we've shifted it around, but we've also squished it in. And so here, this graph is going to be 2x plus 1 squared plus a 2, whereas the other one was just simply x squared. Okay. Okay. Now I have this other one here. It should also be in the notes that were put online. That is working with a rational. So please take a look at that. Online you can actually see this is actually color coded. So you can look at how the graph shifted around and do that. The last thing I wanted to talk about real quick before we end is what happens if instead of going from the formula into its graph pieces, I want to take written into a formula. So here it says use the function g of x equals x squared, and then we want to move the function 3 units to the left and 4 units down. So you have to create this formula. So I'm telling you that g of x is going to be the following. I've got something squared, and I've got an x in it. Now I'm going to move 3 units to the left. So remember, left says that I have to do plus 3. And then 4 units down, so minus 4. And that's all you have to do for that. Okay, it doesn't get any more complicated, no tricks or anything like that. That's all there is. Next one says g of x equals the square root of x. And here we want to reflect across the y-axis and then move it down 3 units. So we have g of x is reflect across the y-axis means we have an internal. So we're going to have the square root of a negative. And then I've got negative x. And then I'm moving down 3. So I'm going to end my radical, and I'm going to move down 3, minus 3. The last one we have is that g of x is the absolute value of x. So we have to reflect the graph across the x-axis, move the function 8 units to the right, and 2 units up. So we have g of x is reflecting across the x-axis is an external reflection, so the negative is on the outside. Then I have my absolute value of stuff. I need to move the graph 8 units to the right. So that means x minus 8. And then I want to go 2 units up, plus 2. So this is everything that you need to know out of section 3.5. It's everything related to your translation units. Do make sure you pay very close attention, read your directions carefully, follow your homework, follow steps, work it slow. And remember, if you have any questions, please make sure that you fill them into the discussion board so that they can be addressed at our virtual classroom.